All right, so yesterday we finished off talking about halogenation. We said that alkenes can act as a nucleophile and attack into elemental bromine as an electrophile. You go through this bromonium ion intermediate where you have this bromine acting as a bridgehead in between two carbons, and then bromide will attack into one of those bottom carbons, slingshot it open, and I referred to this as anti-addition, meaning the bromines are going to be installed on opposite sides. We said that often students will try to show this incorrect mechanism that's similar to the hydrohalogenation reaction where you go through a carbocation, but this mechanism is incorrect, and we have a lot of evidence showing that it is incorrect. So remember with this mechanism not to show a carbocation intermediate. And so we went through a harder example yesterday where we said the pi bond can either attack from the top face or the bottom face, giving this mixture of enantiomers. And yesterday we kind of ran out of time, but I said if it were to go through a carbocation intermediate, we would get 4 different products from this reaction, meaning we could get the products that I have shown in red. We know experimentally we only get the anti-addition product shown on the left. How do we know that they're enantiomers? Does anybody remember the trick? If you notice on the left, so for example over here, this one's R, this one's S, so we flip that stereocenter, and then we flip this one from an S to an R. So oftentimes with these reactions, you will end up with a mixture of enantiomers or diastereomers out of it. So always double check that you're drawing all of your potential products. Oftentimes, instead of drawing 2, you can just write plus En to indicate that you're considering the enantiomer as well. All right, so I'll show you an easy trick for doing anti-addition. Oh my goodness. I wonder if it's this projector. Sorry. Let me close this out. I'm going to double check something. It wasn't doing this last night. All right, let's try this one more time. So trick for showing anti-addition. All right, first thing you always want to do is identify your parent and keep that as is. And then we'll go through a few examples. So your parent could either be the longest chain or it could be your longest ring, but keep that as is. Second thing you want to do is substituents coming off of the alkene. One of them will be turned to a dash or a wedge. Will turn into a dash or wedge. And then last but not least, one bromine will be a dash, the other one will be a wedge. Okay, so let's take a look at some examples of this trick in action. Okay, so in this first example, I'm going to make it like this. We're going to have elemental bromine. We're not going to do the whole mechanism for this. We're just going to try to predict what our product will look like. So first thing I always want to do is identify my parent. So for example, in this one, the parent is going to be the longest chain containing my double bond, right? So I'll highlight that in blue. And then if we think about it, this methyl group coming off of here will be treated as a substituent, right? Okay, so keep the parent as is. So what I mean by that is we've got a 1, 2, 3, 4, 5, 6 carbon chain. All right, that methyl group coming off of carbon 3, you can arbitrarily pick it to be a dash or a wedge. So in this case, I'll pick a wedge, which means the bromine coming off must be a dash, right, in order to form a tetrahedron. All right, now if we think about the bromine coming off of this carbon, should it be shown as a dash or a wedge? A wedge, exactly. And you could show the other product, where maybe instead of that methyl group being in that wedge position, you show it as a dash. The bromine will be a wedge on that position, which means the bromine over here will be a dash. And again, what's the relationship between these? Enantiomers. So what you can do instead of drawing both enantiomers is just draw one and write plus En if that's easier for you. So you can use that trick to kind of speed up the process sometimes. Does that make sense? All right, so let's jump into another reaction. We'll do acid catalyzed hydration. This is actually really similar to hydrohalogenation. And so I'll show you the overall reaction, and then we'll jump into the mechanism and try to predict it. So in this reaction, we'll have an alkene. We'll have water. We'll have catalytic acid. So oftentimes I show that just using H plus in brackets. And you can write catalytic underneath or cat dot. And let's try to predict what our product will be for this reaction. So I'm just going to box this off, and we'll try to use our organic chemistry brains to work through this. So what do you think the first step's going to be? What's the fastest reaction? Acid-base chemistry. All right, so step one, we've got water floating around. We've got acid floating around. Water really quickly is going to steal the proton from whatever that acid is going to be, and we're just going to make our hydronium ion. So this will be step one. All right, does anybody remember what the catalytic acids are that we often use in organic chemistry? Sulfuric. Or we could use phosphoric. Why wouldn't I use HBr? Does anybody know? What could HBr do to that alkene? Hydrohalogenation. So we often don't want the halo acids. We like big bulky acids like sulfuric acid or phosphoric acid. These ones are really nice because the conjugate bases of them really aren't that nucleophilic. However, if you ever see H plus in brackets, you can assume it's one of these non-nucleophilic conjugate bases. All right, so that's step one. We've made our hydronium ion. Let's do step two next. Step two, we've got our alkene floating around. We also have the hydronium ion that was just created in solution. What do you think will happen next? Like we said, acid-base chemistry can occur with pi bonds. It's going to reach out, grab this. Then we have to decide, where's that proton going to go? Is the proton going to go off of the right-hand carbon and give us the positive charge there? Or is the proton going to go in the center and give us our positive charge on the right-hand side? Which one's more likely, left or right? Left one, right? Because it's a secondary carbocation. So I'm just even going to erase that and show that it doesn't really exist in solution. Okay, we still have water floating around in this reaction. So what do you think that water could do? Yeah, it could attack into that carbocation. All right, so now let's try to rationalize what the next intermediate will be. This oxygen will now have a positive charge on it like that. Often when you run these reactions with water, you've got a huge excess of water around. You're using it both as a reagent and a solvent. So if we have water floating around, what do you think the last step is going to be? Deprotonation. So this water can come, steal the proton, we create an alcohol, and we have our hydronium ion. The cool thing with this reaction is, if you notice, we needed hydronium for this first step, and we created hydronium in the last step. What does that tell you about the acid? It's catalyzed and it's being regenerated. So it's going to be catalytic in this case. An important note, I'll go back up here and indicate this, is that water is often your solvent and reagent. All right. So now let's go back and look at step 2. Is this Markovnikov addition or anti-Markovnikov addition? Markovnikov addition, right? So let's just indicate that. Really, for this reaction, you can't avoid Markovnikov addition. In that first step, you always want to form your most stable carbocation. All right. The nice thing with this reaction is it is somewhat reversible, too. So now let's take a look at this. All right, so the reaction we just saw was with an alkene plus water plus our catalytic acid gave us our alcohol, right? However, last term we saw that you could go from your alcohol with catalytic acid to an alkene plus water. These are essentially reverse reactions of one another, right? So the question is, why did we just see formation of the alcohol? Why didn't we have this competing bottom reaction? Does anybody want to throw out any ideas? Cold or hot? All right, so which one would we run hot? The top one or the bottom one? Bottom one. So elimination is favored under high heat. All right, so that's one big thing. So we could control this with temperature and maybe run it a little bit cooler if we want the addition product, run it hotter if we want the elimination product. What's another thing we could do? Dilute or concentrated acid, exactly. So if we think about this, right, another way of describing this, I'm going to erase this, you don't have to in your notes if you don't want to, is think about this as being an equilibrium reaction. Right? If you remember from Le Chatelier's principle in general chemistry, we can push the reaction one way or another by changing the concentration of your reagents, right? So if we want to favor formation of the products on the right-hand side, one thing we could do is increase the concentration of the water, right? If we increase the concentration of the water, it's going to push the reaction to the opposite side. So when we do elimination reactions, do we want excess water around? No, we don't. So now what I want to do is just create like a simple map of this. Like I said, you can keep your notes as is, but sometimes it's a good idea to think this out. So in lab, last term, we started out with cyclohexanol, and we made cyclohexene and water. And that cyclohexene is what we're using in lab this week. And then what we used was catalytic strong acid. And we refluxed this, meaning we heated it under high temperature. So we did high heat. And we had little or no water, because we didn't want the reverse reaction to be favored, and we ran it under high heat to favor the elimination reaction. Conversely, we could, if we wanted to, take our cyclohexene that we made last term, convert it back to cyclohexanol. Again, we'd want catalytic strong acid. You'd want this to be run colder. And what about the water? Well, in this case, we'd want to flood it with a lot of water to push Le Chatelier's principle in the opposite direction. So like I was saying with this reaction, water is often not only your reagent, it's your solvent. That way it's in a huge excess. It actually pushes the reaction to completion. Does that make sense? All right, so now I've got a challenge one for you, because I know everyone likes those. All right, so this challenge reaction has this long chain with an alcohol on it. We've got catalytic acid, but we have no water. So I'll give you a minute to think about what you think would happen for this reaction, but the overall steps for this are going to be very similar to what we just covered. So I'll give you a minute to work on this. So let's do baby steps with this one. What's the first step going to be? Protonate the alcohol, right? So that's definitely the most basic position on this starting reagent. All right, what's the next step in acid catalyzed hydration? Yeah, the pi bond is going to steal one of those protons. So in this case, it can actually steal a proton from itself. All right, so now the question is, will the positive charge, meaning your carbocation, be where the red arrow is or where one of these green arrows are? The red, right? So we know we want to form the most stable carbocation possible. So the positive charge is going to be smack there. That way it's a tertiary carbocation. All right, what do you think could happen next? It could attack itself. So if it does that, basically this oxygen's going to reach in, attack that carbocation center. I will say that these get complicated really fast. One trick I like doing is numbering things. So for example, oxygen being the attacking position, I'll number as 1, 2, 3, 4, 5, 6, which is good. We know 6-membered rings tend to be more stable. So we're going to form a 6-membered ring with oxygen at one of the positions. So I'm going to go through and number this as well. Go 1, 2, 3, 4, 5, 6. Carbon 6 has 2 methyl groups coming off of it, right? That we didn't number but are still there. And then oxygen still has a hydrogen coming off of it. So we'd show that with a positive charge. What will the last step likely be? Deprotonation. And I will show you a trick with deprotonation is if it's a simple reaction, you can just write minus H plus, meaning minus H plus in brackets like that. And you can show your final product that looks like this. What new functional group have we made? An ether. So acid catalyzed hydration can also be used to make some of these ethers. And so as we hit these subsequent chapters in the Klein textbook, we'll see some of these reactions showing up over and over again. But a lot of them you already know how to do just with simple arrow pushing. Does that make sense? All right, so let's make a few notes before we jump on to the next reaction. So the first thing is that it is similar to hydrohalogenation. The acid is catalytic. water is in excess. We said Le Chatelier's principle is favored if we flood the system with water. We have to watch out for stereoisomers, meaning if we're forming a new stereocenter, we're probably going to get both R and S. And the last one is kind of important. This reaction is faster with more substituted alkenes. Does anybody know why? Hyperconjugation, yep, that stabilizes them. The big thing, though, is what do you think the rate-limiting step is for this reaction? Let's go back up and look at it. Do you think the first step, meaning protonation of the alcohol, is rate-limiting? Or do you think formation of the carbocation is rate-limiting? Carbocation formation is rate-limiting, right? The more substitution you have, the easier it is to form that carbocation due to hyperconjugation. Exactly right. So we do have to consider reaction rate. The more substitution we have, the faster it will go. Does that make sense? All right. So I'll show you a problem with this reaction, though, because nothing's easy. All right. Let's say that we have this alkene. We're going to treat it with water, and we're going to treat this with catalytic acid. We said that the first step is going to be what? It's got to be protonation of our alcohol, or in this case, water. Now we've got our hydronium ion. Second step, this alkene is going to reach over, grab the proton from our acid. We know we want to form our more substituted alkene, so it'll favor the secondary carbocation over the primary.
Slow down, like 15%, 20%.
I'm just so excited. All right, what do you think could happen for this next step? Rearrangement? Okay. So we have two options. One, water could add in before rearrangement. So let's take a look at this. So I'll do red arrows with this. So we could have water attack in, or sorry, blue arrows. And I'm just going to follow this kind of down the page. We could lose our proton in this last step. Let me zoom out a bit. There we go. And we could get our alcohol right there. So that's one potential product we could get out from this. However, somebody said this intermediate, meaning this one right here, could undergo rearrangement. Do you think it's going to do a hydride shift, an alkyl shift? What do you think it's going to do? Hydride shift. Okay, so now let's focus on what could happen if there was a rearrangement event. Okay, so maybe we have this green proton over here. This green proton could slide over. That would give us our tertiary carbocation. Now we still have water floating around. This water that's floating around could now attack into the carbocation in the tertiary position. All right, and then last but not least, we could have deprotonation occur. To give us this other product. So this is a significant problem for chemists, right? If I was hired by a company to make this compound, my boss wouldn't be very happy with me if I made a lot of the stuff on the left-hand side, right? Because that'd be wasted material, it'd be wasted time, wasted effort. So we need to figure out a way of avoiding rearrangement reactions with catalytic hydrogenation. So let's make a note. So rearrangement can/will occur, leading to product mixtures. All right. There's a solution, though. It's not the greatest solution, and we'll talk about why, but you'll probably be able to tell. It's to use oxymercuration demurcuration. What do you think the problem is with oxymercuration demurcuration? Sounds like it uses mercury. Is mercury very good for you? Yeah, it's not very good for you, not very good for the environment. Usually people avoid this unless they absolutely have to do it, right? So let's take a look at what oxymercuration is. So step one is to use mercuric acetate. So let's take a look at what mercuric acetate looks like. Mercury is kind of weird. It's a metal, but loves to form organic bonds, meaning covalent bonds. That's also why it's super duper toxic. All right. It's also a pretty unstable reagent. But before we do that, I did want to show some simple tricks you can use to make this a little bit easier. Anytime you see a methyl ketone like this is called an acetate group. And you can abbreviate these as AC. So in this case, we've got acetate groups coming off of each side right there. All right, so in this first step, that bond between oxygen and mercury is somewhat weak. Oxygen, in this case being electronegative, is very happy to steal electrons back from it. But this is a reaction that occurs under equilibrium conditions. Got my lone pair here. So now we've split that oxygen-mercury bond, and we've got our reactive reagent. Oftentimes, what you can call this reagent on the left, meaning the one with the mercury, is you go AC for that acetate group. It's bonded to oxygen, and that is bonded to mercury with a positive charge. And then the piece on the right is going to be an oxygen that is bonded to an acetate group, and the oxygen has a negative charge. So sometimes you may see these written using shorthand notation. All right, now let's take a look at step two. All right, step two is where we have our pi bond, and I'm just going to make up one. And we've got our reactive mercury species. And like I said, the mercury has a positive charge. So what do you think will happen in the second step? Yeah, the pi bond's going to attack that mercury, because we know pi bonds can be nucleophilic. So we're going to attack the mercury. All right, when this happens, something unusual occurs. Just like before, we really like to form our more stable carbocation, but mercury, being as big as it is and having a lone pair, will immediately dump electron density back down into that carbocation center. And what's unusual about this is people will show this as a hybrid. Oh my goodness. Sorry. I don't know if my computer's overheating or if it's the projector or what. All right, so it's a hybrid where the bond between mercury and that carbon is not truly a covalent bond, but isn't a carbocation. So you can show it using either one of these methods. The truth is this bond, this bond right here in the middle isn't a true sharing of electrons. It's kind of shared, kind of not. So we can show it either way, however you want. Yep.
Would it be wrong if we showed it like as a blended hybrid structure with like a dashed line with that?
Yeah, so oftentimes that's a great question. What people will show is instead of showing one or the other, they show it using a dashed line to mercury, like this. Whoops, let me clean this up. And they'll show a partial positive being shared by the mercury atom and that carbon atom. Does that make sense? Yeah. So it always seems weird showing it as a resonance structure because I told you religiously during first term that you can't break sigma bonds with the resonance structure. This is kind of the weird exception to it because there's not really a good way of describing that bond. Yeah. All right, so in the next step, what we're going to do is we're going to take water. Water is going to float around in solution. And in this case, it's going to attack one of the carbons in that three-membered ring. But what carbon do you think is more likely going to be attacked? Do you think we're going to attack this carbon with the purple arrow or this carbon with the green arrow, and why? Purple arrow, right? Because it's got that partial positive character. Okay? So now we'll show this attacking in here. You can show this slingshotting up. Alternatively, we could have had it attack the resonance structure on the left-hand side. Doesn't really matter. So when water attacks in, it still has both of its protons on there. And now we've got this intermediate that is still charged. What do you think will happen to that charged intermediate? Deprotonation, exactly. So just like before, I'm going to shorthand this and write minus H plus. You can assume if there's extra water around, water will be the thing to deprotonate it. If you notice, though, we didn't go through a true carbocation intermediate, which meant it didn't even have the option to rearrange due to that weird three-membered ring state where it's sharing electron density a lot. All right, and then in the last step, we've got to get rid of the mercury. Actually, let's just do it this way. So let's start out with our intermediate that we have shown above. Good thing with this is you don't need to know the mechanism. In fact, it's not totally understood and not even covered in our book. But you use sodium borohydride, and that'll just get rid of the mercury through magic. No, they actually think it's a radical mechanism, and we haven't covered radical mechanisms yet. So magic. But that entire group will pop off and be replaced by hydrogen. So let's make a note that you don't need to know the mechanism. Not at all. But the nice thing with this is it doesn't allow for rearrangements. But like I said before, the big pitfall for this is the toxicity of mercury. and the atom economy is pretty poor, right? We're using a lot of unnecessary reagents that we wouldn't need during a normal catalytic hydrogenation. All right, so let's jump into the next one really quickly. We're not going to do a full mechanism or anything, but it'll help you with the pod. So let's briefly review. So if I treat this with dilute, meaning excess water, and catalytic acid, we're going to create an alcohol, right? So the question is, will the alcohol come off of that red carbon, or will it come off of that green carbon? The red carbon, right? We said it would be a Markovnikov addition. We are creating a new stereocenter, so we do have to be concerned with that. That alcohol could be installed as a dash or a wedge, or I could just be quick and I could write plus En, right? The reaction we just saw, oxymercuration, demurcuration, actually gives you the exact same product. But like I said, it could be used if you want to avoid rearrangement. And the set of reagents can be abbreviated as Hg and then in parentheses OAC, 2. And we can use water as our nucleophile. The cool thing with this reaction is you can use alcohols besides water. So you could use methanol and make an ether, or ethanol, or any alcohol could work there. But for this one, we're focused on making alcohols, so we'll use water. And then in step 2, we use sodium borohydride. Both of these would give you the exact same product. Like I said, it depends on whether or not you need to avoid rearrangement reactions. But then the big question is, well, what if we want the alcohol to come off that green position, meaning the anti-Markovnikov reaction? There's a method to do that. All right, so let's take a look at how you do that. For the first set of reagents, you're going to use borane. The reality is you can't ever buy a bottle of borane. It is super duper reactive. Does anybody know why? Empty p orbital, right? So in order to stabilize the empty p orbital, you essentially have to have a surrogate that can donate electrons to it to stabilize it. Oftentimes what we choose to do that is some sort of cheap ether. So you'll often see this with THF. Or diethyl ether. THF is tetrahydrofuran. Or you can use diethyl ether. This is often abbreviated as ET2O. Either one of these can couple into ether because they've got these lone pairs coming off of the oxygen that can donate into the p orbital. We'll talk a lot more about that when we get into ether chemistry later on. But I did want to explain why there's always THF or diethyl ether in there. All right, so that's the first step of the anti-Markovnikov hydration. The second step is to treat it with peroxide, in this case hydrogen peroxide, and base. Cheapest base is sodium hydroxide, so we'd normally just use that. However, potassium hydroxide occasionally pops up as well. So in this one, instead of adding the alcohol to the more substituted position, we're going to attach it onto that less substituted position, meaning the one off the outside. So this would be anti-Markovnikov. All right, so let's think about why this is occurring. All right, so I'm just going to make up an alkene. So this will be my alkene, and we've got boron floating around like this. Whoops. In solution, a little bit of it will be free borane. But what ends up happening is the electrons in that pi bond are super attracted to that empty p orbital on boron. So that boron very much wants electrons, so it's going to steal it from that pi bond. When that happens, this carbon underneath here develops a lot of partial character and will instantaneously steal this hydrogen. So it's kind of weird. Actually, look, I've got my arrow going the wrong way. It's going to steal the hydride, so we need to show the arrow going that way. And then what we're going to do is show this over and over and over again. And essentially, that BH2 will get replaced with an OH. The reality is, this set of mechanistic details is super long, super tedious, and I decided just to scrap it from this term because I don't feel like we learn a whole lot from it. However, that being said, what I will do is post a supplemental video that walks you through each of these steps. But if I were to show you this mechanism, it would take like a whole lecture period, and people just kind of glaze over. So watch supplemental video. With that, normally a hand will pop up and they'll say, do you expect us to know this on quizzes and exams? And I will say, no. It is really, really long. So I'm just going to leave it at that. However, it's a neat reaction for getting the anti-Markovnikov hydration products. I do, on the other hand, want you to know what reagents you need to accomplish this transformation. Does that make sense? All right, tomorrow at 1:30 p.m. in this room, we'll do a supplemental review session. So basically, I'll just pull problems from the books. You can come prepared with questions, and you can just use that time to go over practice stuff. Yep. That's a good question. It probably won't be, just because it'll be a hodgepodge of different people asking questions. But if you have questions, you can always email me, and I can help you via email. Yep.